So, most of these are going to involve what you guys saw, not yesterday, last time, I think it was the very last, example we did. Matter of fact, flip back in your notes, the one that we had to factor. It's not going to involve factoring per se, but it's going to involve that last step. If you take a look at your notes of that last step, where we had the parentheses like this, and then it was equal to 0, does that sound familiar? And then you set each parenthesis equal to 0. A lot of that is going to be involved in today's. Just not going to have to use the factoring techniques, other techniques. So here's example 1. One plus sine x equals 2 cosine squared of x. So it isn't real easy to solve an equation that involves two different trig functions. We have sine and cosine. Usually not the easiest thing to do. So you could, this is involving this first subtopic, equations involving identities. So it's a pretty safe bet we're going to have to come up with some identity that, there's probably a lot of identities we could use, but the point is we want to use an identity that will give us all of the same trig function. So you're taking a look at this one here. Is that the one you're looking at? What's the identity for cosine squared? There's actually 3 of them. And the one in particular that we would probably want to use is the one that involves only sine. Remember, there's cosine squared minus sine squared, or there's 2 cosine squared minus 1, or plus 1. So this one would be 1 minus 2 sine squared. That would be the one we would want to use. So rewrite this.
Are we evaluating it?
No, we're solving the equation. Yeah, we're solving the equation. But it's much easier to solve trig equations if the whole equation is in terms of the same trig function. Right now we have sine and cosine. So we want to try to get this in terms of sine. So this is going to be 1 plus sine of x equals 2. Now make a substitution using the appropriate identity.
Minus sine squared of x.
1 minus, this is the Pythagorean identity actually, 1 minus sine squared. So we still have a squared term, but the point is it's all in terms of sine now. This is sine, and you know what, I think I lied to you earlier, this one actually is going to have to be factored. Darn it! Wait a minute. Yeah, it's going to have to be factored. Alright, anyway. Okay, this one's going to have to be factored. Most of the rest of them aren't. If it's going to have to be factored, though, one side has to equal 0. So let's get rid of these parentheses. It's going to be 2 minus 2 sine squared of x. 1 plus sine of x. So we're going to want to get one side equal to 0. It doesn't matter what side is equal to 0, but when you're factoring a quadratic expression, it's best if you can have the quadratic term positive. So I'm actually going to add the 2 sine squared to the left side and then subtract the 2 to the left side, just so that we can end up with a positive quadratic term. So it's going to be positive 2 sine squared x plus sine x minus 1 equals 0. And don't let the signs throw you off. This factor is just like a normal quadratic equation with factor. Just imagine that these sine squared and the sine, just imagine that those are big x's in them. And so it just look like this, 2x squared plus x minus 1. If you can factor this expression, 2x squared plus x minus 1, then you can factor this one because it factors the exact same way. So if you need to, and it's fine if you do, if you need to factor this first, just using normal quadratic expression, and then use that as a pattern to factor this. So how would you factor 2x squared plus x minus 1? If it factors, maybe it doesn't, I don't know. One's going to have to be a 2x, the other one's going to have to be an x. And then we know that the last two are going to have to be a plus 1 and a minus 1. Somewhere we're going to have a plus 1, and somewhere we're going to have a minus 1. It's going to be 2x minus 1, and x plus 1. So if you want, you can use this as a pattern for factoring this. It's quadratic in form. It's going to have the two parentheses equal to 0. What's it going to be? What's this first? If we're using this as a pattern, what's this first parenthesis going to be? 2 sine x minus 1. Good. And then sine x plus 1. And it is so critical that this equals 0 because we have a product. This multiplied by this is equal to 0. That means that one of these or both of them have to be 0. So you take each expression in the factors and set them equal to 0. 2 sine, and this is exactly what we did last time. I think the bell might have rang, so we might not have been able to finish it, but this will actually be good. We can finish this up. We set the first factor equal to 0. You set the second factor equal to 0. Oh, notice early on in the problem there was no restriction on x. X didn't have to be within a certain interval. So what does that mean? How many solutions here? An infinite number of solutions. Do you remember how it was last time we represented that? How did 2 pi k, we just keep going around the circle an infinite number of times. So we're going to have to do that here. So how do we, let's focus on the one on the left right here. What are we doing there? Add 1, divide by 2, exactly. So sine x, if you add 1 and then divide by 2, you're going to get a 1/2 over here. So sine of x equals 1/2. And I gave you 2 suggestions on how you could finish this up. You could either just use inverse sine on your calculator, which is fine. I will provide you a copy on the exam. I think it'll be the back page. I'll provide you a copy of the unit circle. So let me see if I got one here. If it were me, I'd rather use the unit circle because the calculator acts as a function. It'll only give you one of the correct answers. So you'd be better off using the unit circle. So if you're doing the inverse sine of 1/2, you need to look around the unit circle and find angle measures whose y value is equal to positive 1/2. Y value equal to positive 1/2. And unless stated otherwise, the default is radians. So always state your angles in radians, unless it says not to. So what are we looking at? Where do we have angles whose y value is 1/2? 5 or 6? 5 pi over 6. So those are 2 of the solutions from this piece of it. X equals pi over 6 and x equals 5 pi over 6. Remember though, these are not restricted to within one revolution of a circle. So plus 2 pi k and plus 2 pi k, where k is an integer. Alright. Other one, sine x equals 1. Obviously we're going to minus 1. We're going to get sine x equals negative 1. So to the unit circle. Say again? Yeah, we need to find an angle whose y value is negative 1. That actually only happens once on the unit circle. We have a y value of negative 1 all the way down here at 3 pi halves. So for this piece of it, x equals 3 pi halves plus 2 pi k. Well, that was sure great. keep going. Example 2. I think this one will be more apparent which identity we're going to have to use. It's sine 2x minus cosine x. Remember, we're facing a similar problem that we were facing in the problem above. It's not easy to solve a trig equation if there's two different types of trig functions on there. Unless we can factor. This is going to be a different type of factor. Obviously, which identity are we going to use here? The double angle for sine, the sine of 2x, the double angle for sine of 2x. That was not too hard to remember. Yeah, 2 sine x cosine x. That one's pretty easy to remember. So 2 sine x cosine x minus cosine x. What's saving us here is that this equals 0. This is pretty nice. Now, take a look at both sides of this expression on either side of the minus sign. We have 2 sine x cosine x minus cosine x. What do they have in common? Cosine x. And this is pretty usual. You end up doing this quite a bit, factoring out a common expression. Rather than factoring a quadratic expression like this is kind of unusual. This type of factoring you're going to see a lot more of, where you just factor out a common term. So again, if you take a look at both of these, they have cosine x in common. So if you factor that out, what's left over? 2 sine x minus 1. So the only reason we're able to solve this, even though we have two different trig functions, the only way we're able to solve this is because it forms a product that equals 0. If this had formed a product that didn't equal 0, there are other ways to solve it that we're not going to go into. So since the product equals 0, do the exact same thing we did in that problem above. Take each factor separately, set it equal to 0, and solve. I'm going to give you guys a chance. Go ahead and try that. Take each factor, set it equal to 0, solve them separately. Remember, this is not restricted to one revolution, so there's an infinite number of solutions for each. But go ahead and try it. So on the unit circle, cosine x equals 0 twice. When do you have x values equal to 0 on the unit circle? When x equals pi over 2, and on the other side of the unit circle, not at the bottom, at 3 pi over 2. You'd still do 2 pi k on these. Yeah. Didn't we just do this one? This looks really familiar. We're going to get sine of x equals 1/2. Yeah, we already did that one. Add 1, divide by 2, you get sine of x equals 1/2. So just if you weren't paying much attention to the last one, sine x equals 1/2. You got to find y values on the unit circle that equal 1/2. So you have one here at pi 6, other one at 5 pi 6. So x equals pi 6 and 5 pi 6 plus 2 pi k. So we're not done really using identities. We're going to get into that second objective. That second objective is also going to use some identities. The second objective is called something with multiples of angles, solving equations involving multiples of angles. So let's go here and then here.
So about the identities here, where you switch the sin 2x to 2 sin x cosine x, how does that work out exponentially?
This here
Yeah.
to this. That was the double angle from lesson 7. 7.2, I think. That's a double angle identity. We learned sine of 2x was equal to something. We learned cosine of 2x was equal to 3 somethings. And we learned that the tangent of 2x was equal. Those sound familiar at all, the double angle identities? They were. Does anybody have their notes out? It was section 7 point something. 7.3? Yeah, it was 7.3. So that double angle stuff came from 7.3. The sine of 2x was equal to 2 sine x cosine x. The cosine of 2x had 3 versions. Cosine squared minus sine squared, or 2 cosine squared plus 1. 1 minus 2 sine squared. Something like that. The tangent one,
Got 2 forms.
yeah, and then if those angles were the same, it became. So let's get into the second objective, and we're going to be in the second objective for a while because it involves quite a bit more than this first one. So it's called multiples of angles. So here's example 3. They're not harder to solve, they're just a little bit different. 2 sine 3x plus 1 is equal to 0. This one isn't going to involve an identity because we don't know an identity for the sine of 3x. So the point here is just to isolate the trig function, use inverse trigonometry to get rid of the sine function, and then we can isolate x by dividing by 3. So, subtract 1, divide by 2, you're going to get sine 3x equals negative 1/2. If you subtract 1, divide by 2, you get sine of 3x equals negative 1/2. Well, we don't know a specific formula for the sine of 3x. We could maybe split this up into the sine of 2x plus x and then use the sum identity. That would make it a lot more difficult to do it that way. The point is to solve for x, right? There's a couple of things here to get rid of. We need to get rid of sine eventually. We'd have to get rid of 3 after that. So what's a way to get rid of the sine? So we can do inverse sine. So 3x is equal to the inverse sine of negative 1/2. So inverse sine of negative 1/2. I'd go to the unit circle. We need y values of negative 1/2. It's going to be 7 pi 6 and 11 pi over 6. So 3x could equal 7 pi over 6, or 3x could equal, what was the other one? 11 pi over 6. But here's the thing that you need to do at this step, and this is where some students make a tiny mistake. We're not restricted to one revolution of a circle. So in this case, the inverse sine is not acting as a function. It's acting as an inverse operation. that means we could have multiple answers. So we add the 2 pi k now. Now how do we solve for x? Divide by 3. Now watch closely to how this happens. Yes, you divide that by 3. Yes, you divide that by 3. And yes, you have to divide that by 3. That's why it's important that you put the 2 pi k before you divide by this value. And here's why this has to happen, you guys. I need you to listen carefully. Put your pencils down for a second. Plus 2 pi k just means that the period repeats itself every 2 pi. And isn't that what normally happens with the sine or cosine? The period repeats itself. But the thing is, this is not the sine of x, this is the sine of 3x. Now we haven't talked about this in a while, but if I were to ask you to graph y equals sine of 3x, what effect does that 3 have to the graph? It affects the period. Does it lengthen it or shorten it? Remember, inside the function is opposite. So instead of taking 2 pi k to repeat the cycle's been cut by a third. So it repeats itself every 2 pi third k. Does that make sense? So it repeats itself more often because the period of that function has been decreased by a factor of 3. That's what's happening here. Same thing over here. Divide everything by 3. So, oh man, 7 pi over 6 divided by 3? How the heck do you divide by 3? The denominator. You want, because dividing by 3 is the same as timesing by a third.
Yeah, so would it be 1 over 6?
It would be, so let me write this, 7 pi divided by 3. That's kind of what this is saying.
Oh,
that's
the
same as timesing by a third.
Yeah.
So it'd be 7 pi over 18 plus 2 pi k thirds. And on the bottom, x equals 11 pi over 18 plus 2 pi k thirds. Let's make this part B some example because it has a lot to do with this one we just did. This one's going to involve both the use of an identity and this idea of using multiples of angles. So solve sine 3x cosine x minus cosine 3x sine of x equals 0. Remember, I said this was going to involve the use of an identity. Test is Friday. Sine 3x cosine x minus cosine 3x sine of x. If you have your notes out, I'd give you a hint. Look in section 7.2. This involves an identity that we talked about in 7.2.
Same as sine alpha minus
Yeah, the key here is you recognize that pattern. Sine, cosine, cosine, sine. Wasn't that one of our patterns? Sine, cosine, cosine, sine. Which one was that the pattern for? The sine. It's one of those, it wasn't the double angle, it was the sum or difference of two angles involving sine. In this case, it's the difference because it's sine, cosine minus cosine, sine. So just consider that one of these is your alpha, the other one is beta. Do you see that identity in section 7.2 in your notes? Let me write it out for you. The sine of alpha minus beta. This was the identity. Is sine alpha cosine beta minus cosine alpha sine beta. That's the identity. Well, sine of 3x minus. Yep. So we're going to put this back together using this difference identity that we talked about in 7.2. This is going to be the sine of 3x minus x is equal to 0. So the sine of 2x is equal to 0. Now what? Inverse sine, yep. So 2x is equal to the inverse sine. All right then, so where? You got to think where on the unit circle do you have a y value of 0? Y value of 0 means you're on the x-axis. So you're on the x-axis. Yes, but you're missing one. 0, 0 pi, x equals 0, x equals pi. We actually don't need 2 pi because we're going to take care of that. So that's your 2x. 2x equals 0 plus 2 pi. Okay. 2x equals pi. Plus 2 pi k. Zero and 2 pi are the exact same thing, so we don't need to include that. We'd actually take care of that with this one here. 0 plus 2 pi. Now divide by 2. What's an interesting color? Hold on. There we go. So, x equals still 0 plus pi k, and here x equals pi halves plus pi k. Let's go on to example 3.4. This is going to involve a different identity. Well, a different not a different identity, sorry, it's a different multiple of an angle. Still the same.
Why don't you just have 0 on the option? Like, where do you get x equals 0?
X equals 0.
Pi k.
This one right here?
Yeah.
Because 0 divided by 2 is still...
Yeah, but where do you get 0 for that possibly?
Well, the inverse sine of 0 right here.
Might that be pi? Oh, I guess it is 0 as well.
Yeah.
Yeah, I see it now.
Yeah, does that make sense?
So what?
Yeah.
Can you write that in just as like x equals pi k, or should it be 0 plus pi?
Pi k would have also worked, but just so you see that there is a solution there, I'm going to put a 0. Example 4. Ooh. Tangent. We haven't done one with tangent. There's 2 more after this. Square root of 3. Tangent x over 2 minus 1 equals 0. So we're not actually going to have to use an identity here. We're just going to have to solve this by isolating tangent, then taking an inverse tangent, and then solving for x by multiplying both sides by 2. So first step is to isolate the tangent function. That's not so hard. Add 1, divide by square root of 3. So tangent x over 2 is equal to positive 1 over square root of 3. Now you can rationalize it if you want to. You don't necessarily have to, because we're not going to use this as part of our answer anyway. We're just going to have to use this inside the inverse tangent. And matter of fact, for that reason, I would leave it like this, in this form, without rationalizing it. X over 2, here's why. X over 2 is going to equal the inverse tangent of 1 over square root of 3. So if you're going to use your unit circle, it'd be better to leave it in this form without rationalizing it. On the unit circle, what's the definition of tangent? Sine over cosine, or y over x. So we need to find angles who would have a y over x value. Y value 1 divided by square root of 3, or if the sine was equal to 1, cosine square root of 3. So you can use your unit circle. It takes a little more thought. The calculator would work here. Who's got the calculator on? What does the inverse tangent of 1 over square root of 3 tell you? 30. That's in degrees, and that's fine to use your calculator for degrees. But remember, the default would have to be radians. So it's pi over 6. But that's the one drawback. I've mentioned this a couple of times. Your calculator will only give you one of the answers because it acts as a function, one input, one output. There's another spot on the unit circle where the tangent's positive.
7 pi over 6.
Which quadrant is it? It's the third quadrant. So if the calculator is giving us an answer of 30 degrees, we'd have to go into the third quadrant where 30 degrees is the reference angle. So 30 degrees is the reference angle for this angle right here. So that's also a possibility, 7 pi over 6. So x over 2 equals pi 6 plus 2 pi k. And then x over 2 can also equal 7 pi 6.
Pi thirds also the answer?
Pi thirds? That would be the square root of 3 over 1.
Okay.
Yeah, you're close. So are you using the unit circle to try to? Yeah, you're close. Yeah, that's good to be able to do that. It's hard for most people. That's good if you're practicing that. But yeah, that would be inverse tangent of the square root of 3. Last step. Multiply everything by 2, including that 2 pi k. So multiply by 2, multiply by 2, multiply by 2. So x what does x equal? Yeah, that's going to be pi over 3, exactly. Pi over 3 is 4 pi k. And then x equals 7 pi over 3 plus 4 pi k. All right, you guys ready for this? I'm going to add an additional piece onto this problem. List all solutions actually write that all on want you to tell me. Tell me 6 of the solutions. If there are infinitely many, let's use this to tell me what 6 of them are. We already know 2 of them. What are 2 exact solutions? 5 over 3, 7 pi over 3. There's 2 of them, 4 more to go. How do we find any more than just that? We can add 4 pi. Now what is k? K could be 1, k could be 0, k could be 2. So just, if k equals 0 though, that's just going to give us these 2. So we've already technically used k equals 0. So we could use k equals 1. So I'm going to use k equals 1 for both of these. That means it's going to be pi thirds plus 4 pi or 7 pi thirds.
Is that how you rewrite that?
Oh no, we're going to have to combine these.
Okay,
Yeah, we're going to have to combine these. So pi thirds plus 4 pi. Yeah, we're going to have to get a common denominator of 3. So this is going to be pi thirds plus 12 pi thirds. If you combine that, you get 13 pi thirds. Same thing over here. So if you just imagine it's going to be 12 pi over 3, 12 pi plus 7 pi is 19 pi. So 19 pi thirds. Hey, we have 4 solutions total. We could use k equals -1. We could use k equals 2. I'm going to use k equals 2. K equals 2. That means it's going to be pi thirds plus 8 pi. 7 pi thirds plus 8 pi. Or I guess we could have just added 4 pi onto these. Would have been the same thing. Anyway. So how do we add pi thirds to 8 pi? Just like that, huh? Yeah, it's going to be times by 3 over 3, so that's 24 pi over 3. 24 pi over 3 plus pi over 3 is 25 pi thirds. Same thing with this one. 8 pi over 3, if you multiply that by 3 over 3, it's 24 pi over 3. 24, oh man, 24 pi plus 7 pi is 31 pi over 3. Do we have all 6 of them? Let's see. 1, 2, 3, 4, 5, 6. Ooh, we got it. Okay, 2 more. Example 748. That's what it seems like, doesn't it? But it's only example 5, right? 4, 5. Holy moly! All right. Well, it's been taking a while. Solve the equation. So what are we thinking? Yeah, I would. Well, I would much rather not have cosecants and cotangents in there if we can avoid it. What is cotangent? Cosine over sine. You're right. It's cosine over sine.
No, I just changed cosecant.
And we could do that. We're gonna have to do that. So if we change cotangent to cosine of x over sine of x, plus 3. What could we do to cosecant? What's that?
Why don't you just change the use of the pattern to that in that one and change this
Okay, that's also a possibility. Take a look at 7.1 notes. 7.1. Yeah, let's see. Cosecant is 1 over sine squared. That's true. So we could write this as 1 over sine. Let's see, 1 over sine squared of x. That could work. And this is one of these things where, kind of like verifying an identity, we could try something. If we can't get very far into it, we might have to go back and try something else. 7.1 notes. Quickly go to 7.1. Flip back in your notes. We had this identity here that you wrote down, sine squared of x plus cosine squared of x equals 1. And then we kind of rearranged this to equal a few different versions of the Pythagorean. Do any of those have any bearing on this problem? So wait, say that one that you guys just said right there. 1 plus cotangent squared equals cosecant squared. So even though this is true, these identities are correct, it might not have been the best to consider going this route. What about using this route here?
That was too easy.
Why does this one look better? We need to understand why this one looks better.
Because it has both cosecant and cotangent part.
We say that again?
It has both cosecant and cotangent. Like,
Exactly.
those are the ones we're looking for.
If we change this to this, what's the use of doing that? Then we already have everything in terms of cotangent. So I'm actually going to erase this. Try it again. This cosecant squared of x can change into this. 1 plus cotangent squared of x equals cotangent of x plus 3. Get everything on one side. So cotangent squared of x minus cotangent of x minus 2 is equal to 0. Well, here it is again, more of this quadratic factoring. We just can't get away from this stuff. You might get to the point where you can just straight up factor this, but for the time being, it'd probably be best if you just compare this to an actual quadratic expression and then factor that. X squared minus x minus 2. How's that factor? X minus 2. Ooh, I said something and wrote another thing. X minus 2 and x plus 1, yep. So you can use that as a pattern to factor this. Cotangent minus 2, cotangent of x plus 1. It's forming a product. The product equals 0. That means both pieces of the product have to equal 0. Cotangent x equals 0, or cotangent minus 2 equals 0. Cotangent plus 1 equals 0.
How come both have to equal 0?
Because we don't know which one does indeed equal 0. In order for a product to equal 0, one of these has to be. And since we don't know which one, we assume that both of them are. Yeah. Oh man, we haven't really dealt much with cotangent recently. He's probably feeling bad. That's why he showed his ugly head in this problem. Cotangent of x equals 2.
Maybe that's why he's doing
Cotangent
that,
of x.
because you're calling him ugly.
Yeah. Yeah. Cotangent x equals negative 1. I don't know about you guys, but I'm not really liking cotangent here. We can still do it, but
There's a better way.
could be.
Well, let's not do that.
Is this true?
Yes.
Or am I just making stuff up?
No, that's a lie.
Or am I lying to you guys? Is cotangent equal to 1 over the tangent?
Yeah.
All in favor, please show by the raise of, oh, wait.
All opposed.
1 over tangent of x equals -1. What's the use of doing this? Well, I don't know about you guys. I'm more comfortable with tangent than cotangent. You guys probably are as well. We need to still manipulate this slightly. How can we clean this, the one I'm circling, how can we clean this up a little bit? Yeah, multiply both sides by tangent and then divide by 2. If we do 2 steps in one, we're going to have the tangent of x equals 1 over 2. There we go. Do you see what we did there? We're doing some mathematical trickery.
So does that
Witchcraft.
Does that mean you can do the same thing on the other one?
Yeah. So on the other one, if we multiply both sides by the tangent, divide by -1, we're going to get tangent of x equals -1. Yeah.
Isn't this an easier way to do that since cotangent and the fraction reverse, you just do 1 over the number on the other side?
Yeah, it's essentially what we did there, yeah. You can do that. I just like to do things the long way, you know? Now what? Inverse. Well, one of these we could probably do without using the inverse. This one here, we might be able to just reason our way to it. The definition of tangent on the unit circle is y over x. The only time y over x is going to equal -1 is if y and x are the same. One's just negative, one's just positive. You guys following here? So where on the unit circle would you have a y value that's equal to an x value, but one's positive, one's negative? The second quadrant, 3 pi over 4, and then there's one in the fourth quadrant. Did you guys all hear that? So, I mean, the calculator could have told us the same thing, but it might have been quicker just to reason our way through that one. This one is going to be x equals, and I just forgot what you guys told me, 3 pi something? 3 pi over 4, and then x equals 7 pi over 4, and I don't believe this one had any restrictions on it, did it? It did not. So, plus 2 pi k plus 2 pi k. Alright, dang it. Tangent of x equals 1/2. Getting my calculator running. Hold on a second. It isn't going to be a nice angle, I don't believe.
No.
Inverse tangent of 1/2. Ooh. That's in degrees. Let me put mine in radian mode. Hold on a second. So here's the thing that you can do. If it's not a nice angle that doesn't convert well between radians and degrees, turn your calculator to radian mode. This is the answer in radians. I know it doesn't have pi in it because pi is multiplied in there. So what we're going to have to do here is, well, we could divide by pi, but it still wouldn't turn into a nice fraction either because the corresponding degree wasn't a nice whole number degree. So here's what we're going to do. I just lost it. Where to go? calculator. Where'd you go? 0.46. That technically is in radians. Plus what? But you have to realize something. There's one more answer to this. Remember, the calculator only gives you one answer? So, what other quadrant would be positive for tangent? Tangent's positive in the first quadrant, obviously, and this is in the first quadrant. What was it? Third quadrant. So we're going to have to go into the third quadrant now. How do you go from the first quadrant to the third quadrant? What do you add? I mean, you add pi, right? So if we take the answer that we already had, this one here, and you add pi, then it's 3.6 roughly, plus 2 pi k. In this case, because it was such a weird angle, yes. It's not a nice normal angle like 30, 60, or 90. It's a possibility. Let me answer it this way. It's a possibility. One quick one, then we're done. Actually, you know what? We're going to be done here, and here's why.